So we have been seeing a lot of biasing circuits, and we have seen how the circuits work under simulation. So we have two more biasing circuits type which have to be completed. The next two types we will see today. So the next one is collector emitter feedback bias. So this is actually an extension of collector to base biasing. So we have seen collector to base biasing in the last class, where instead of having base resistor connected to VCC, we'll be connecting base resistor to the collector terminal of transistor. So the position you see RB is connected here, but usually RB will be connected here directly. But instead of doing that, I'm connecting this, and I find that this is going to effectively reduce the value of my stability factor. So we have already seen in common emitter amplifier, when you have an emitter resistance RE, the stability factor is reducing. So already in collector to base bias, the stability factor is very less. So if we want to even more reduce it, I'm going to combine both the techniques. So I'm going to add a resistance between collector and base terminals RB, and I'm also going to add resistance RE in the emitter side. So this is actually no longer a common emitter amplifier because the emitter is not grounded. The emitter is grounded through a resistance RE. See, input you give to base, output you take at collector, but emitter is not directly grounded. I have a resistance RE in the emitter to further reduce the value of my stability factor. So as we have discussed in previous classes, stability factor value has to be as small as possible, which will account for the variation in your collector current. So S value, whatever you get from the formula, it should be as small as possible. So far the different biasing circuits we have seen fixed bias, uh, we have seen collector to base bias, fixed bias with emitter resistance. Then now we are seeing collector emitter feedback bias. So all these are different combinations of circuits tried out to ensure that the stability factor is going to be always kept as low as possible. So see, this is going to be a combination of, I'm going to apply collector feedback as well as emitter feedback. See, feedback means you are going to add the resistance between the input and collector, between emitter and collector. So see here, between RE is going to act like an emitter feedback resistor, RB is going to act like a collector feedback resistor. So two resistances I'm going to add for collector side feedback and emitter side feedback. So what is the advantage I'm going to gain from these resistors? I'm going to have a very good decrease in the value of stability factor. So that is the gain I'm going to make. Okay, so see here, the collector feedback is provided by connecting a resistance RB between collector and base. So as I told before, usually RB will be connected between base and VCC in fixed bias, if you remember. But in collector to base bias, RB is connected between base and collector. So this is going to act like a feedback resistance. Okay, and in emitter side also, I'm going to provide a resistance RE between emitter and ground, which is going to provide the necessary emitter feedback. Okay, so this is the circuit configuration of collector emitter feedback bias. So remember, this is the combination of collector feedback and emitter feedback. So remember, you should not by heart the circuit. You should remember the concept. If collector to base feedback means what resistance I'm going to add. If I'm going to have emitter bias means what resistance I'm going to have. If I'm going to combine both, what will be the diagram be? Everything should be very, very clear, and you should be very clear on the circuit concepts. So both the feedbacks are used here. One is the feedback through the resistance RB, another one is the feedback to resistance RE. Both are going to control the collector current. Okay, so both are going to keep the collector current in check. So if IC is going to increase, IB will decrease. If IB is going to decrease, IC will also decrease. So in that way, it is a feedback process. So if collector current is increasing by variation of temperature, the base current starts reducing. Since base current is going to decide the collector current, if base current is reducing, then IC also has to reduce as per the transistor logic. So that is going to be a feedback loop happening here, which will ensure that any variation in IC is handled in a quite efficient manner when the temperature is going to rise.